Good morning, everyone. I'm Zhihao Zhang. I will present our fourth paper, SkySync. This work accelerates file synchronization or file sync using collaborative data generation. The author represents institutions including Xiamen University, Shanghai Jiao University, Alibaba Cloud, and Tsinghua University. Cloud computing is moving toward a new model called sky computing. Sky computing distributes workloads across multiple clouds. This requires moving and syncing data frequently over wide area networks. Our main goal is making this inter-cloud file sync fast and efficient. To save network bandwidth, data sync is currently widely used. Data sync only transfers modified parts of a file. However, finding these modified parts is called data generation. Data generation creates a big bottleneck on both the client and the server. There are two main ways to do data sync. The first way to do data sync is phase size trunking. A popular example is rsync. In its workflow, the server first splits the old file and calculates a weak and 32 bits and strong 256 bits checksum for all chunks and sends this list to the client. Next, the client uses a sliding window to check the new file byte to byte. It does exhaustive calculations and to find matches and verify strong checksums. It also does many hash table lookups. Finally, the client sends the literal or data bytes back for the server to reconstruct the file. This method places a very heavy computational burden on the client. The second way is content-defined trunking. A popular example is dsync. Here, the client casts the new file into variable-sized chunks, calculates their weak checksum, and sends the list to the server. The server finds the matches, computes strong checksum only for matched chunks, and sends tokens back. After verifying, the client sends the data to the server. Compared to rsync, dsync has some advantages. It requires less overall computation because strong checksums are only calculated for matched chunks. It also shaves part of the computational burden from the client to the server. And however, computing all those weak checksums and hash table lookups remains a heavy task. We measure the time spent on different types. We found that for 100 megabytes micro benchmark file, checksum calculation and search include hash table lookups take up to 95% of the total sync time. To address this, we initially applied hardware acceleration utilizing vector instruction sets. But hardware acceleration helps, but it does not reduce the volume of checksum calculations. We look closely at modern storage system. The conventional storage layer already maintains rich metadata for internal management purpose, including data integrity and error detection. By analyzing various storage types, we categorize the available metadata. The first is block devices, such as those utilizing device mapper variety, maintaining cryptographic hash trace using secure hash algorithm. A modern file system including ext4, B3FS, and ZFS apply checksums like CRC32 and the secure hash algorithms to their data blocks. Similarly, distributed systems like the HDFS and BlueStore generate and store checksum to verify data integrity. Upon every read operations, we can reuse this existing storage layer metadata to reduce the expensive checksum calculation during file sync. Based on this insight, we propose SkySync. SkySync uses a collaborative approach inside the client and server storage system, there is existing metadata within the storage layer. Instead of doing heavy math to compute new checksums, our checksum calculation and searching module extracts and reuse the storage layer metadata directly. Then the network modules use a communication protocol to exchange the checksum list, matching tokens and literal bytes. By reuse this metadata, we reduce calculation on both endpoints and speed up the file sync process. And we design SkySync to extract storage layer metadata using 3 distinct methods. First, for local block devices and file systems like ext4 and B3FS, we utilize user-based tools by leveraging utilities such as file system Verity and B3FS programs. SkySync directly extracts checksums without requiring complex kernel modifications. Second, for distributed storage systems such as HDFS and BlueStore, our system relies on system application programming interface. For instance, SkySync fetches checksums directly from the Hadoop name node. Third, for specialized systems like suitable tools or interfaces, we implement custom parser functions. These custom functions allow SkySync to directly read and interpret on-disk metadata formats to ensure functionality, although they require slightly more maintenance. And to conduct data generation, we must compute checksums efficiently. For fixed-size trunking, SkySync server directly uses fixed-sized checksums extracted from the underlying storage layer. However, applying this to content-defined trunking presents a major change. The dynamically generated variable-sized chunks typically do not align with the fixed storage chunks. For example, in the figure, the underlying storage layer might provide existing checksum for neat 4 kilobyte blocks. But the content-defined trunking algorithm determines trunk boundary based on the file content. This means the boundaries of the variable-sized chunks labeled as trunk R in the figure will cross and overlap the boundaries of the original 4 kilobyte storage chunks labeled as trunk F in the figure. To solve this specific boundary misalignment, we develop a fast checksum combining algorithm within the SkySync architecture. We first read the checksums of each fixed trunk from the storage layer, and then we mathematically derive the weak checksums of the misaligned variable-sized chunks without needing to scan every single byte. Our fast checksum combining algorithm leverage the algebraic properties of the CRC32 algorithm. The CRC32 checksum of a large data sequence can be mathematically computed from the checksum of its constituent parts. When new variable-sized trunk overlaps a fixed-sized storage trunk, we identify the small string of differing bytes located at the overlapping boundaries. We refer to this differing section as bytes X and bytes Y in the figure. Instead of processing the entire variable trunk from scratch, we only calculate the partial CRC32 checksums for the small differing byte sections. Typically, these differing bytes account for less than half of the total trunk size. Next, we append the appropriate number of trailing 0 bits to the pre-existing storage block checksum to correctly align their lengths. Finally, we merge these combined checksums together using simple XOR operations. This mathematical combination completely skips the process of sequentially reading and recalculating the majority of the raw file bytes. Next, we improve trunk searching. Traditional methods like rsync or dsync use a slow multi-level lookup process. They first check a 16-bit hash, then a 32-bit weak checksum, and finally a strong checksum. This requires searching through many pointers, which takes a lot of time. SkySync uses a flat hash table with a direct cuckoo hashing scheme. To find a target string, we reuse its CRC32 checksum to directly opt into possible bucket positions in the hash table. Client and server storage might be heterogeneous, which means they are different from each other. To solve this, SkySync uses a communication protocol that negotiates sightings in the initial request. There are two main differences. First is the trunk size mismatch. When using fixed size trunking, the server always sends the checksum list first. Therefore, the client adapts to the server's trunk size. If the client has smaller trunks, it simply combines its smaller checksum to match the larger trunk size of the server. On the other hand, when using content-defined trunking, the client splits file first. In this case, the server adapts to the client's trunking parameters. A second is a checksum type mismatch. SkySync handles this by prioritizing common and efficient types, such as CRC32 for weak checksums and SHA for 256 for strong checksums. If the client and server support different strong checksum, SkySync aligns with the party that computes the checksum first. We test SkySync on Alibaba Cloud Server with B3FS. We use a 500 megabits per second wide area network with a 35 millisecond round trip time. We compare SkySync with rsync and dsync. We use micro benchmarks and 5 real-world data sets. And our results show that SkySync improves the total end-to-end sync time by 1.1 times to 2 times, specifically for these real-world data sets. Our design reduces the total computation time on the client and server by 19.2% to 43.7%. And we also check the network traffic. SkySync keeps the network traffic at the same level as the baselines. Also, extracting metadata is an order of magnitude faster than recalculating it. It only takes a tiny fraction of the total sync time. To conclude, file sync is bottlenecked by expensive expected data generation. We noticed that modern storage layers already have the checksums we need. SkySync reuses this metadata. It provides fast checksum calculation, direct trunk searching, and a smart communication protocol. SkySync improves sync performance with no significant network penalty. Okay, thank you for your attention. Please feel free to ask any question you may have.